supersonic motion of gravitating body in a gas cloud. And here there is a schematic picture of the model. So you can see it? Not really. Okay. You can see the uniformly distributed gas here that flows past the gravitating body represented by the accretor here, and the gas is attracted by the gravity of the central body. And if we consider the ballistic orbits, we can define the accretion radius such that gas approaching the central body would collide on the accretion column and will be left with insufficient kinetic energy to escape from the gravitational potential of the central body. In the same way, we can define the mass accretion rate as the mass flux passing through the circle with the radius of equal to the accretion radius. And if we combine those equations, we obtain the mass accretions, the Bondi-Hoyle-Littleton mass accretions in the standard version, which depends on the mass of the central object, the density, the velocity, and the sound speed of the medium. This formula has been used in many applications. For example, can be used to compute the mass accreted on a compact object in a binary system. And, but there are also many ingredients that can change the value of the mass accreted on a central object. For example, in particular in this study, the authors want to study how the relativistic Bondi-Hoyle accretion can be modified by the presence of small obstacles. To do that, the authors use KEFI, which is a relativistic magneto-hydrodynamics code, to resolve the relativistic hydrodynamics equations on a space-time Schwarzschild black hole. They consider a spherical grid centered on the Schwarzschild black hole and assuming an axial symmetry. They use natural units. They measure the length and the time in unit of mass, define the Unicode for the mass if equal 1. This is the computational domain where Rx is the radius of the event horizon of the black hole, and delta theta and delta R are the resolution of the grid. These are the parameters used to define the gas cloud. We have the gamma, adiabatic index, the speed, the sound speed, the density, the Mach number, and MB is the number of the obstacles. The initial velocity is chosen to represent a homogeneous gas that fills the entire domain and which flows along the z-axis. Moreover, the authors compute the mass accretion rate by using a spherical mass detector at the event horizon and evaluating this formula, where VR is the radial component of the velocity. The peculiarity of this study is that they introduce the presence of small bodies. These small bodies are characterized by are rigid, static. That means that they don't move during the simulations. They are randomly distributed, and they are supposed to be circle along the RZ cross sections with a radius smaller than the accretion radius. To study how these objects change the mass accretions on a black hole, the authors perform simulation with different number of obstacles, 0, 5, and 10, and considering different value for the Mach number, 5 or 4. Since the flow is supersonic, each obstacle creates a shock, a bow shock front, and where the gas density increases and the gas velocity decreases. And after a while, those fronts start to interact each other, forming a more complex structure. And here I show you the magnitude of the velocity for each simulation at time equal 1000 m. From left to right, we can see the simulation without obstacle, simulation with 5 obstacles, with 10 obstacles, and the first 3 are with Mach 5, and the last one with 10 obstacles and Mach number 4. As you can see, increasing the number of obstacles, the structure becomes more complex. Sorry. Here I show you the mass accretion rate evolution for only for the simulation with Mach number 5, and considering 0 rigid bodies represented by the blue line, with 5 orange line, and with 10 the light blue line. In all cases, the accretion rate starts from 0 and saturates around T equal 200. But in the case without obstacle, which is the standard Bondi-Hoyle-Littleton accretion model, the accretion rate evolves smoothly. While adding obstacle, if we add obstacle, we have that the accretion rate fluctuates around a constant value. Moreover, I want to point out that just adding 5 bodies, the accretion rate increases by 45% with respect with the standard Bondi-Hoyle-Littleton accretions. And doubling the number of obstacles doesn't change a lot the mass accretion rate. Now I show you the mass accretion rate evolution for simulation without obstacles, the solid line, with 10 obstacles, the dashed lines, and the red line represents the simulation with Mach number 5 and blue with Mach number 4. If we consider the solid red line, we can notice that increasing the number of obstacles from 0 to 10 has the same effect to decrease the Mach number from 5 to 4. So, to conclude, this is an interesting article because it's the first study of Bondi-Hoyle-Littleton accretion in the presence of obstacles. They show that the presence of rigid bodies increases the mass accretion rate, and that the effect of decreasing the Mach number, that means the initial velocity, is equal to the effect of increasing the number of obstacles. So that's all.
Any questions?
Just said that if this is true for stellar mass like
This is in units, so just changing the, okay, they use geometrized units for the simulation, but changing the mass of the central body and the density and the speed velocity, you can have a different scenario, physics scenario. And here I reported, here it's a supermassive black hole, an intermediate massive black hole, and a stellar massive black hole.
And so physically, the rigid bodies will be different things for, of course, for supermassive black holes, for stellar. So did they mention what are these small rigid
They can
bodies?
represent different things. They can be a dense cloud of gas, a passing star, or also a bubble created by a feedback due to supernova explosions.
So they didn't mention if with this model they can constrain on the discussion about the dust storms, also the accretion disk around the supermassive black hole, this clumpy or...
No, but this is the first, so they mentioned that they want to study in more depth, because also in that case they use these obstacles that are torus in 3D space, so it's not really physics. And also they are fixed, so in reality cloud, stars, or whatever move during the simulation, so it's just the starting point.
Other questions? Okay, no other questions, so let's thank
Thank you.
And now we have the second speaker of today, Senator. The title. Which one? And Sina will talk us about 10 billion years of brightest cluster galaxy alignments.
Okay, good afternoon everyone. I know everyone have a nice holiday, so let's begin. And now the aim of, first is the aim of this paper. Now it's known that the major axes of the brightest cluster galaxy are often elongated in the same direction as the cluster they reside. However, most studies of the BCG alignments have only focused on the relativity nearby place and redshift less than 0.1. So this aim of the aim of this paper is examining more distant cluster to have a better understand how this alignment have evolved over the time and the process that have shaped the galaxy over the history in the university. So first is the sample selection. The custom member was selected based on their location of the red sequence. The red sequence is well-defined region in the color and luminosity space co-occupied by the relativity earlier type galaxy, and then they fit the red sequence with a straight line using the model of minimum absolutely deviation to exclude the possible alternate. And those galaxies within 5 sigma of the red sequence were assumed to be the custom member. In this way, they select a sample of 16.5 distant galaxy cluster for the Hubble telescope archive. This selection represents the most massive galaxy cluster at the redshift range for 0.19 to 1.8, corresponding to the distance for 2 to 10 billion years. Here is 4 images for the Hubble telescope. Their redshift is A is 0.2, B 0.4, and C 0.6, and D 0.5 respectively. So the second second work that they do is calculate the position angle of the galaxy and the cluster. And each galaxy shape and the orientation in the plane of the sky was measured for the resonance of the Hubble telescope image by fitting a single component Seeker profile to the surface brightness, and then using the Goldfish software, and the orientation of each cluster principal axis was determined by computing the moment of inertia of the distribution of the red sequence. So the uncertainty of about the uncertainty of the position angle, they use the bootstrap resembling model. And here, 1 sigma uncertainty is typically about 10 to 20 degrees. There are 13 clusters with the uncertainty of position angle larger than 25 degrees was excluded for the sample. So finally, 15 clusters were leaving for the subsequent analysis. In order to have a further check, they also analyzed the galaxy and the cluster in the cache sample, which is a published sample with the mass model was divided for the gravitational lensing, reaching 3 to 4 magnitude greater than the brightest member. They measured the orientation of 2,137 individual galaxies and the principal axis of 22 clusters in the class sample. And they found that the position angle applied for the moment of inertia was the gravitational lensing, have external agreement in general. So this is the histogram of the orientation of 2,137 galaxies in the crash cluster sample, and the x-axis is the x-axis sigma is the acute angle between the projected major axis of each galaxy, and they are the cluster they reside. If the galaxy and the cluster they are perfectly aligned, then the theta will be equal to 0. So for this image, we can see that there is a uniform distribution between 0 degree to 90 degree, and is consistent with that. There is no preferred orientation in the cluster galaxy. However, if we only consider the brightest cluster galaxy, there is a very strong tendency of this galaxy share the same orientation with the cluster they reside. And this histogram also shows that the BCG at the redshift larger than 1.3, which is the most distant galaxy. And then there is also a very strong tendency that can be seen that this galaxy and their host cluster share the same orientation, even though in the very earlier epoch. So finally, about the BCG, they make a conclusion that the brightest galaxy in the cluster have been aligned with their surroundings for at least the past 10 billion years. There are several possible theories for the origin of the BCG alignment. The first is an anisotropy in flow of matter and flow into the galaxy along preferred direction. And the second one is primordial alignment with the surrounding matter distribution at the time of galaxy formation. Further is the gravitational calculus that gradually align galaxy with the local tidal field. And finally is some possibility and is combine some possibility of those. So, but however, the paper presented in here is still not allowed to differentiate between these different scenarios. So that's it. Thank you.
Any question for Stina? Apparently no question.
They mentioned something about the local universe from Sloan, for example, where they have much larger.
No, they only use the image for the Hubble telescope and combine the sample they select with the cache sample. And the cache sample is for another paper, and they not present in here.
Other questions? Let's thank again the speakers of today. You're free to go. Please just remind sign the.
Così la potete saltare il giorno del 26 febbraio, visto che un sacco di gente è alla scuola di Gaia. Perché ad esempio io sarei il 5, solo che non ce la faccio, cioè sono lì tutta la settimana, non penso di farcela. Però quindi dovrei chiedere spostamenti, non so se c'è qualcun altro caso, se c'è un problema.
Ma per ora nessuno ci ha detto nulla, se però nessuno ci ha detto nulla. Però sì, penso di sì, perché alla fine non sanno fatto no, cioè nel senso, come diceva Lorenzo, che con il giornale dell'anno scorso eravamo, cioè siamo arrivati soltanto con una lunghezza sappiamo perso subito.
Fatta molto bene. E poi
Cioè, a scuola di Gaia andiamo, penso, sì, è vero anche che ci sono parecchie persone, non so, tra il primo e il secondo anno, quanti assetti ci saranno, però
Se loro ci sono.
no, certo, però io sicuramente
Non ce la fai a fare
cioè, più che altro io ho questo problema che vabbè, cioè, posso chiedere uno scambio
non c'è una
però dicevo se magari effettivamente siamo tanti assetti magari può
sì, per ora appunto nessuno ci ha chiesto nulla, però se vuoi fare un cambio
io tra l'altro avrei bisogno di farlo dopo perché passo per le Canarie a febbraio, quindi cioè anticipato poi
possiamo anche
selezionare
cioè, allora se voi se sappiamo il 26 possiamo far shiftare tutto il
no, esatto,
non penso che sia anche in questa maniera ne faremo 11 possiamo anche
vabbè insomma io te lo dico poi cioè fateci sapere se caso mai sarà
provo a sentire ci siamo sicuramente problemi, ripeto, tanto
grazie.
Sì, sembra.
questa era di qualcuno perché non è cioè non è nel set metà da me.